Thank you. Thank you very much for that introduction, and thank you for the honor of being here today to speak to you on this very important topic. I very much appreciate the opportunity, and I thank the organizers for inviting me. What I'm going to be talking to you about today is geospatial data integration for forest carbon monitoring. And although I appreciate that many of you may not know much about forest carbon monitoring, I want to use it as sort of an example of the kind of work that myself and a number of colleagues and institutions here in Mexico are involved in, where integrating large data sets are concerned, which brings into play issues of data sharing, issues of data management, issues of institutions working together. So I hope you will see this forest carbon monitoring topic more as an example of how groups can successfully, I think, work together to bring data together to find solutions, answer important questions. All right, just an overview of my talk. I'll first present a bit of background on my institution, the Woods Hole Research Center, which is actually where I work. I went to the University of Michigan for my academic career, and now I'm at the Woods Hole Research Center, which I'll talk more about in a moment. I'm also here representing a project called Mexico Red, which I will also talk more about in just a moment, and give you a bit of background on forest carbon monitoring and the history of forest carbon monitoring within my own institution and in the context of MRED. I'll talk a bit about the challenges to geospatial data integration in the context of this effort, specifically about the forest carbon monitoring work we're doing here in Mexico, our current activities, as well as the future directions where we hope to take this work, particularly with an emphasis on airborne LiDAR, a really interesting and relatively new sensor for which a lot of data is being collected in Mexico. And finally, I'll conclude with some thoughts and some lessons learned where geospatial data integration is concerned. So a few words about the institution that I come from, the Woods Hole Research Center. We're a small, nonprofit research institute located outside of Boston, Massachusetts, roughly 13 scientists like myself. Our mission is to seek science-based solutions to the world's environmental and economic challenges through research and education on forests, soils, air, and water. Our work focuses mostly on the carbon cycle, with an emphasis on global land management and the competition for land. And because we're small, we work with a number of partners, ranging from NGOs to research centers to governments, such as the government of Mexico and even the United Nations. So a bit about the project that I'm involved in specifically here in Mexico. It's called Mexico Red, or MRED. And RED is an acronym, R-E-D-D. It stands for Reduced Emissions from Deforestation and Forest Degradation. And this is a policy mechanism that is being discussed, being negotiated at various levels, specifically within the United Nations, to try to compensate actors, such as national governments, for maintaining their forests intact, specifically their stocks of forest carbon. So as part of this project, we're working with a number of institutions to help the government of Mexico prepare for this policy once it actually takes hold. And it hasn't sort of taken hold yet, but we hope it will soon. And so this is a large project. It has a number of different institutions involved. It's actually led by the Nature Conservancy and the Woods Hole Research Center and Rainforest Alliance are partners. It has a number of specific activities ranging from public policy to communications to financial architecture, as well as the nuts and bolts of monitoring changes in forests and forest carbon stocks across the country. Not surprisingly, we're working with a number of institutions within Mexico, particularly institutions within the government, including CONAFOR and CONABIO, as well as the Mexico-Norway Project and a number of others, all working together to prepare Mexico for RED. Now, not surprisingly, given the history of my institution in terms of work focused on the carbon cycle, my activities are focused on the forest monitoring piece to this puzzle and trying to help the government of Mexico advance its capacity to monitor its forests across the nation. And we're working in 5 what we refer to as early action areas. And these 5 early action areas are spread across 8 different sites from Chihuahua, Jalisco, 3 in Oaxaca, Chiapas, as well as the Yucatan. So you can see here in this region of southeast Mexico, there are a number of sites where this project is focused. And these sites were chosen so that they are intended to be representative of many of the ecosystems, many of the issues on the ground that are relevant to RED. And so although our work is primarily in these early action areas, the work is meant to be relevant at the national level. So a bit of background on my work and the work of my institution where forest carbon monitoring is concerned. In 2012, my colleagues and myself produced the first map of above-ground forest carbon at a resolution of 500 meters for the entire pan-tropical belt. And you can see a portion of that fell within Mexico right here, at least the part that falls within the tropics proper. Also in 2012, some colleagues and myself released a data set, a very similar data set focused on the U.S., the lower 48 states of the U.S., a similar above-ground map of forest carbon stocks, in this case at higher resolution, now at 30 meters. Okay? So these 2 different projects prepared us for what would be our work here in Mexico. And that involved developing the first high-resolution map of forest carbon stocks for the entire country, also at a resolution of 30 meters. And that map has been recently developed, and the data has been recently released. It's freely available. And we're now working on how to integrate new data sets into this effort to make this map even better. And I'll spend some time talking about this work itself, as well as these new data sets, particularly with an emphasis on airborne LiDAR that we hope to integrate into this effort to advance this work. So as I said, I want to use this as an example of data integration, and particularly talking about some of the challenges associated with data integration. And so here I'd like to spend some time speaking to what some of these challenges are, not only in the context of this particular project, but really in the context of any project of this size, of this scope, with this many partners, with this amount of data. And I see the challenges really as being technical as well as institutional, okay? And again, these aren't challenges that are unique to Mexico or unique to this project, but certainly they're relevant in terms of our work here. So where technical challenges are concerned, there's a number of them that I'd like to touch on. The first being data availability, okay? This is always a question. Is the right data available to address the problem at hand, whether it be field data, okay, data from the ground, or whether it be geospatial data, okay? Is the data out there that I need? Then there's the challenge associated with minimizing the mismatches that are often present in these data sets. Too often, particularly for projects across large areas, we're being forced to use data to answer a question for which it was not originally intended. And here in Mexico is a great example. We're using National Forest Inventory data, which originally wasn't designed to be integrated with remotely sensed data, with geospatial data. So we have to try to work to minimize the mismatches between these data sets, to get these data sets to speak well with one another. Another technical challenge is understanding uncertainty. Okay, increasingly we need to work harder to understand error in our data sets, that is, get a better handle on how good our data products are. And most people don't like to talk about error because it tends to suggest that the data might not be good. If there's error in the data, well then the data is not very good. But of course there's error associated with all data sets. And so as long as we understand that error, as long as we're able to quantify that uncertainty, I think that's what's important. There are also, in addition to technical challenges, there are institutional challenges, okay? Again, I put data availability in this category. Lots of institutions have data, but are they willing to share the data with those who are trying to answer the questions, okay? So the data may exist, but we just can't get our hands on it. There are, of course, infrastructure limitations. That is to say, there's limitations associated with availability of software and hardware and maybe the internet, okay, that have to be overcome. There are, of course, capacity limitations, and capacity limitations aren't unique to any one country. There are capacity limitations in the US. There are capacity limitations here in Mexico, and we have to try to work together to overcome those. And finally, there are challenges associated with communication. For example, we're dealing with a communication challenge right now because I don't speak Spanish very well. And our wonderful translators are helping me to communicate with you. But challenges aren't just in terms of language. They can be in terms of institutions who have different cultures, who struggle to communicate well with one another. Okay? So throughout the rest of my talk, I'm gonna be sort of returning to these challenges and thinking about, in the context of this forest carbon mapping work, how we've tried to overcome them. Okay, so the first issue we grappled with where mapping forest carbon across the whole country was concerned was one of data availability. What are the best data sets out there to make such a map? Well, forest carbon is really a mass. We're talking about estimating a mass, a weight of carbon contained in the biomass of vegetation above ground. So this is a three-dimensional problem, all right? So we need to address it with data that deals with this three-dimensional nature. And so we used two different data sources. We used, in this case, radar data from a sensor called ALOS Pulsar, which is a Japanese radar satellite or radar sensor. Why radar? Because radar is an active sensor that's sensitive to particularly the vertical structure of vegetation, okay? But by itself, we knew that radar would not get the job done, so we had to integrate other data sources, and we had to bring in some Landsat data. Specifically, Landsat data that's part of the Vegetation Continuous Fields product of Matt Hansen from the US. This data is particularly sensitive to horizontal structure. Okay, so together, between these two data sets, we address the need for three-dimensional structural information. Now, we also needed field information, in situ information from the ground to calibrate our models, okay? Well, we're fortunate in Mexico that Mexico has a fantastic national forest inventory, some 26,000 points across the country that were collected from 2004 to 2007. And within each of those points, CONAFOR has used the information there, together with some 350 allometric equations, to estimate the amount of above-ground carbon present, okay? But now, as I mentioned earlier, these data were not designed to be integrated well with remote sensing, okay? So this presents a challenge in and of itself. But the overall goal was to use these field data together with our radar and Landsat data and generate a map for the whole country. And to generate that map, we first needed a model. And the model we chose is based on a data mining algorithm called Random Forest. It's an open source algorithm, a regression tree algorithm that's available in the R statistics package that many of you might be familiar with. Our response variable in this modeling exercise was obviously the above ground carbon density as derived from the National Forest Inventory data, INFIS. And our predictor variables represented a suite of different measures of structure derived from the radar data, derived from the Landsat data, okay? We developed this model, and here are our results. Now, I realize this presentation is not intended to be very technical, but I want you to have a sense for how we did, all right? Well, we found that in flat terrain, okay, we did reasonably well. Okay, we have an R-square of roughly 0.52, which is good, but not necessarily great. And a root mean square error of some 14 tons of carbon per hectare, which is also good. The range of carbon above ground in Mexico is between 0 and roughly 100 to 120 tons. Now, on steep terrain, we didn't do as well. Okay, we have a much lower R-squared. Okay? So the map currently is good, but it's not great. And this is at the pixel level. This is a 30-meter resolution map. All right, so at the pixel level, there's a lot of uncertainty. However, when we look at coarser scales, when we aggregate the information in the map to coarser scales, we see a lot of improvement. And here what we're looking at is information at the state level. Here we're looking at the average amount of carbon in each of the Mexico states within the INFIS data compared to the data in the map. And now here we see a very nice relationship. Okay, an R-square of 0.98. Okay? And similarly, when we look at total carbon, we also see a very nice relationship. So we see that at the pixel level, the map has some problems, but at coarser scales, it's better. We can also look at the national level, and this is an example of the actual map at the national scale. And we've actually developed a very nice poster from this map, which I have copies of. I don't have enough, unfortunately, for everyone, but I do have some copies to share for those that might be working in this area. And if we look at the results at the national level, we see that within the map, if we just look at areas where our Landsat data says we have canopy density greater than 0, we see that we have 2.21 petagrams of carbon. Now, if we instead look at the INEGI land cover data as a source for our forest cover map, we instead see that we have only 1.53 petagrams of carbon. All right? Now, if we compare those results from the map to the results actually being reported by Mexico as part of the United Nations FAO Forest Resource Assessments, both in 2010 and the upcoming one in 2015, we see we have between 1.6 and 1.69 petagrams of carbon. So when we use the INEGI data as a forest mask, we get a result that's very close to what's being reported using the INFIS data and using the INEGI data. However, when we use a different source of information for the carbon mask, we get a different result. Again, we see the results of data integration issues, okay? If we define forest differently, then we're going to end up with a different result. And so we need to, this is one of the challenges that we need to work through, for example, with respect to data integration. So as I've said, the map is good, but it could be a lot better. And so what are we going to do to try to improve it? Well, it's a very exciting time, as I was telling some folks here this morning, I think, to be working with geospatial data here in Mexico, because there is a tremendous amount of new and exciting data being collected, and that type of data is airborne LiDAR. And airborne LiDAR has a range of uses. Airborne LiDAR in general is sensitive to the three-dimensional structure of whatever is present on the landscape. And here is an example of an image produced from an airborne LiDAR. You can see, you essentially have a three-dimensional view of what's present on the ground. And it has a whole range of applications outside of forest carbon, okay? And those include mapping habitat and biodiversity, mapping, producing digital elevation models, looking at faults and subsidence and landslides. Also, for those of you, some of which are on the panel, working offshore, there's a utility for bathymetric surveying, water surface roughness, shoreline and coastal change, as well as atmospheric, urban, and archaeological applications. So there's a whole range of applications outside of forest carbon, making this data very exciting. So I'd like to just spend a little bit of time showing you all what's available for Mexico, what's going to be available for Mexico, and particularly here in the southeast. So this is just our carbon density map as a background. And here are those early action areas where our MRED project is focused. And within the MRED project alone, we're collecting some 1,500 square kilometers of airborne LiDAR data. A combination of transects and quadrats within these different early action areas. Okay? So right there is a lot of data in and of itself. The data is being collected right now by Carto Data, which is a Mexican provider out of Guadalajara. They're doing a fantastic job, and just a week ago, I received the first hard drive with data from the Jalisco region here, and I'll show you a bit of that in just a moment. But there are also other data sets. In 2012, NASA, the US space agency, flew all the transects that you see here in red. Okay, and just a couple of weeks ago, this data was released online. I've had a chance to look at it, and it's fantastic. The data from the MRED project will also eventually be released online, freely available to anyone. Additionally, we have data that was collected recently by the US Forest Service. You can see a few green points here. These represent 3 by 3 kilometer blocks where airborne LiDAR data was collected. Additionally, this year, here on the Baja Peninsula, the Forest Service is collecting additional data, which is very nice because before now, there was no data yet collected of this kind on the Baja Peninsula. And last but not least, CCGSS has just completed collection of a LiDAR data acquisition, I'm told, right here in Tabasco. So On the whole, there's a tremendous amount of data available for Mexico. To the best of my knowledge, all of it is going to be freely available for anyone to use. If we zoom in here on the southeast region, you can get a better sense for all the different acquisitions, all right? Even in the United States, where we have a lot of data of this kind, it's unusual to find in such a reasonably small area so much data of this quality and with this many applications. And so I think this is really an exciting time for all of you to be working in geospatial sciences and geospatial applications here in Tabasco and in Mexico. I'd like to now just show you some of this data here from Jalisco. As I said, I just received the first hard drive of these data a couple of weeks ago, and I'd like to show you a small area located right here. I don't know how well you can see this, but we have both LiDAR data and digital orthophotography being collected, and here you see an orthophoto draped over top of a digital elevation model that was produced by the LiDAR. Here you see the intensity information, that is the backscattered energy from that LiDAR draped over this orthophoto and digital elevation model. And you can see here, these are agricultural fields, and what you see are the individual trees, hedgerows of individual trees that are showing up quite clearly. Here is the DEM, the digital terrain model produced from the data. And here is the digital surface model, which includes the vegetation and any structures that might be present. So it's a fantastically detailed data set. The resolution is on the order of 1 meter, okay? And when we take the digital surface model and subtract it from the terrain model, we can look at canopy height. And of course, that's what I'm interested in. So here is a map of canopy height. You can see in this location it ranges from 0 to about 15 meters. And when we look at that relative to our existing map of above ground carbon, we can see some nice relationships. We can see where we have the tallest trees. We have, of course, the highest amounts of carbon. So what we hope to do to make our map better is to incorporate this airborne LiDAR data, to integrate this new state-of-the-art data source. So how are we going to do that? Well, there's a fundamental problem that we're trying to overcome, and it really gets at why our map isn't as good currently as it could be. And that relates to this problem of mismatched data. What we're starting with is sparse field measurements, relatively few field measurements from the National Forest Inventory. And what we're trying to do is make a map where we have information for every 30-meter pixel everywhere. All right? And we use a model. We use a model to accomplish that. But guess what? There's a big data gap. There's a big gap here between having few field measurements and generating a wall-to-wall map where we have imagery everywhere. So what we hope to do is we hope to integrate the airborne LiDAR data to fill this gap, okay? To generate models that first relate the field measured data to the airborne LiDAR, and then models relating the airborne LiDAR data to the wall-to-wall imagery to improve this map, okay? It's a problem of data integration, and this is how we hope to solve it in the context of this mapping exercise. So some concluding thoughts and some lessons learned, and I'd like to come back to the slide I talked about earlier, focused on challenges. And I spoke of technical challenges, data availability, data mismatches, understanding uncertainty. And I'd like to just say a few words about how we've overcome some of these challenges in the context of this project, and how more generally I see us being able, as researchers, as applied scientists in the geospatial field tackling some of these issues. First of all, where data availability is concerned, at least here in southeast Mexico, I think there's a lot more data becoming available than you might have actually guessed. And of course, LiDAR data isn't the only data source out there, but there's a lot of free and interesting and high quality data that's going to become available, freely available. There will always be issues of data availability, but there's more and more good data all the time, and I think you all will be the benefit of some of that here very soon. Where minimizing the mismatches between data sets is concerned, a few comments. First of all, I think it's important always that we clarify our goals and objectives at the outset of a project. And this may sound a bit simplistic, but the more we know about where we want to go, the better off we will be choosing the right data sets and making them work as well as they can work for our particular project. In the process, we also need to be careful to understand the limitations of our data. The more we understand the limitations of our data, the better we will be at using the products of our analyses for what they were intended for. Okay? For example, in the case of our carbon map, at the pixel level right now it's not very good. All right, so we shouldn't really be using it at that level, but at coarser scales, it's all right. Where understanding uncertainty is concerned, I would argue that error is a good thing if we understand it. That is to say, uncertain knowledge is power, okay? When we don't understand uncertainty, it can be a real problem. But if we understand it, if we know how uncertain our data is, how uncertain our products are, we're in a much better position. So we shouldn't be afraid, I guess. We shouldn't be afraid of error. What about on the institutional side? Well, first of all, there's the issue of data availability. As I mentioned earlier, we often have cases where institutions have very good data, but they're not necessarily willing to share it. And I would just say that the issues that we're grappling with, particularly on the environmental side, are urgent issues. They're urgent issues, and we all have data that we should be doing a better job of sharing, because certainly we all have projects and papers that we want to finish and complete, but there are others out there that have ideas about how this data might be used. And so we need to make sure that we put our data in a position for others to work with it and get the most out of it quickly so that we can find answers and work towards solutions. Just quickly wrapping up here, this is my last slide. Where infrastructure limitations are concerned, I think the best thing we can do is we can promote open source solutions, whether it be software, whether it be data. In our work, we try to use open source software as much as we can so that other people can reproduce the work without spending money on expensive data sets. Capacity limitations. We're very good at holding workshops. It's something that I do a lot, something that a lot of us do a lot, but I think we need to work beyond workshops towards expert exchange programs, actually having researchers shared among institutions for longer periods of time. I think geo-user groups are another way to bring people together in a region, communicating online, meeting periodically to share experiences, knowledge. And finally, the issue of communication. I think more often than not, if we listen more and speak less, we'll be much better off. And so that's what I'm going to do now. I'm going to speak less and I'm going to listen more to all of you. Thank you so much.